So this is lesson 6, solving double angle equations from unit 5, trig identities and equations of the grade 12 advanced functions course. So in this lesson we're going to be looking at how to solve double angle equations, something like this over here. At this point in the unit, I'm hoping you already understand how to solve equations like this. This is called a linear trig equation, so it would just be like sine x equals a half. You know how to use your reference angles and cast rule to find all the answers within a given interval. In this lesson specifically, we're going to look at how does the process change when the angle is no longer just x. What if it's 2x that we're solving for? How does that change our answers? How does that change our process algebraically? And most importantly, what's the relationship between these two equations and their answers? So make sure you click the link in the description. Get the blank copy of the lesson so you can follow along and fill it out as we go. And let's get started. So let's start by going through this investigation where we're going to use the graphs of y equals sine x and y equals sine of 2x to answer some questions that will hopefully by the end of it give you a good understanding of how you're going to solve double angle trig equations. So this graph right here, y equals sine x, you should be very familiar with this graph. You know, a normal sine function completes one full cycle between 0 and 2 pi. The period of it is 2 pi. The highest it ever goes is 1, the lowest it ever goes is -1. The graph of y equals sine of 2x, you may not be as familiar with it, but hopefully you remember that this transformation parameter right here, we normally call it k, performs horizontal stretches and compressions by a factor of 1 over the k value. So since k is 2, how would it transform the graph of y equals sine x? It would do a horizontal compression by a factor of a half. So the horizontal length of one cycle is going to be half as long as that of y equals sine x, right? It completes one full cycle in pi radians instead of 2 pi radians. And so between 0 and 2 pi, this function now completes 2 complete cycles. Let me just remind you of this in Desmos as well. So here in Desmos, I have a sine function graphed for you. I have one cycle of this outlined in green. And look how, as I adjust the k parameter, how that affects the horizontal length of the cycle, right? So how it affects the period of the function. So notice that as I'm adjusting the k value, that is affecting the horizontal length of that one cycle I've outlined in green. So I think at this point you understand now that the k value affects the period of the function. And it affects it specifically by a factor of 1 over the k value. So let's use these two graphs to answer some questions. The first question here says, what is the period of both of the functions above? So we've already talked about that. And how many cycles between 0 and 2 pi radians do the functions complete? Well, the sine x function, the period of it, remember period is the horizontal length of one cycle. The horizontal length of this one cycle is 2 pi. So for sine x, the period is 2 pi. Therefore, it completes one full cycle between 0 and 2 pi. So one cycle. How about for y equals sine of 2x, right? This does a horizontal compression by a half. So we can calculate the period of any transformed function by doing 2 pi divided by the absolute value of k. So 2 pi over 2, which is pi. And if we look back at the graph, notice the horizontal length of one cycle, which I outlined for you before. The horizontal length of this cycle, so the length from here to here horizontally, is now pi. It's half of what it was for sine x, and that's because of the k parameter. So how many cycles does it complete between 0 and 2 pi? If we look back at the graph again, it completes 2 cycles between 0 and 2 pi. So it completes 2 cycles. Part B. Looking at the graph of y equals sine x, how many solutions are there for sine x equals 1 over root 2? And I should specify how many solutions between 0 and 2 pi. Right, when we're solving trig equations, often the domain that we want the answers between is specified. So how many solutions between 0 and 2 pi are there for this equation here? How many angles for sine have this ratio? So I know we know how to solve this algebraically, right? We learned that earlier in this unit. To solve this algebraically, you figure out, first of all, where is sine positive, right? Because we have a positive sine ratio here. Sine's positive here and here. You place the reference angle that creates a sine ratio of 1 over root 2 in those two quadrants. We get pi over 4, pi over 4. And then you calculate the principal angle for both of those. So principal angle of this one is pi over 4. Principal angle of this one is 3 pi over 4. So there's two solutions. We can get them algebraically. But I think it's also very beneficial to understand how we can solve this graphically. So let's look back at the graph of sine x, and let's figure out when is this graph equal to 1 over root 2. And the approximate value of 1 over root 2 is 0.71. So let me just draw a horizontal line through y equals 0.71, and that'll give you a good indication of when the sine function is equal to that. So now that I have the horizontal line drawn through y equals 0.71, we can see the sine function is equal to that in two spots, right here and right here, at an x value of pi over 4 and an x value of 3 pi over 4. And those are the two solutions that I showed you we could get algebraically as well. So what we just figured out from the graph is that sine of pi over 4 and sine of 3 pi over 4 are both equal to 1 over root 2. So there's two solutions between 0 and 2 pi for this equation right here. The important part of this lesson is going to be part C. Part C says, looking at the graph of y equals sine of 2x, how many solutions are there for sine of 2x equals 1 over root 2, which is that approximate value 0.71. And once again, we only want the solutions for x that are between 0 and 2 pi. So let's go back and look at the graph of sine of 2x, and first of all see how many solutions are there, and what are the solutions? What angles can I double so that the sine ratio is 1 over root 2? So here's the graph of sine of 2x, and remember between 0 and 2 pi, the function does 2 cycles. And within each cycle, there are 2 answers. Let me just draw that horizontal line to show that to you. So the horizontal line through that approximate 0.71 value. So looking at that horizontal line and where it intersects our graph of y equals sine of 2x, you can see that sine of 2x is equal to 1 over root 2, that 0.71 value, here at pi over 8, here at 3 pi over 8. So those are the 2 times in the first cycle that it's equal to 1 over root 2. And it's going to be equal to that 1 over root 2 value 2 times in every cycle. So 2 times in the first cycle, 2 times in the second cycle, so again here at 9 pi over 8 and 11 pi over 8. And in the third cycle, it would be equal to 1 over root 2 twice more, fourth cycle twice more, and so on. But we only want the answers between 0 and 2 pi, and this function does 2 cycles between 0 and 2 pi, so we get 4 answers. Our 4 answers are pi over 8, 3 pi over 8, 9 pi over 8, 11 pi over 8. So let's fill that in. So between 0 and 2 pi, we figured out there were 4 answers to this equation. There were 4 solutions. The angles that when doubled have a sine ratio of 1 over root 2, where pi over 8, 3 pi over 8, 9 pi over 8, and 11 pi over 8. And we could answer part D now as well. So when the period of a function is cut in half, what does that do to the number of solutions between 0 and 2 pi? Well, if the period's cut in half, that means it's going to do twice the number of cycles between 0 and 2 pi, which means you're going to get double the number of answers. So it'll double the number of solutions. In part 2 of this lesson, we're going to be solving double angle equations algebraically. But before we do that, I just want to backtrack to the graphs of sine x and sine of 2x so that you can understand the relationship between the answers to those equations that we were working with. So here's the graph of sine x, here's the graph of sine of 2x, and what I have circled are the solutions to the equation sine x equals 1 over root 2 and sine of 2x equals 1 over root 2. That's what we worked through in the investigation. What's the relationship between these answers, though? The relationship between this pair of answers and this pair of answers is pretty straightforward to see, right? Since this function has been horizontally compressed by a factor of a half, each of these points are going to be half the distance from the y-axis, right? Their x values are cut in half. If I do pi over 4 cut in half, I get pi over 8. If I do 3 pi over 4 cut in half, I get 3 pi over 8. So those are fairly straightforward to see the relationship. But once we are able to get these two answers, how do we generate these two answers? Well, if you have a good understanding of periodic functions, we know that periodic functions have a pattern of y values that repeat at regular intervals. And the intervals that they repeat at is called the period of the function. And what's the period of this function? Well, we talked about this already, the period of this function. We always calculate the period by doing 2 pi over the absolute value of k, so 2 pi over 2 is pi. So the period of this function is pi. It means it repeats a cycle every pi units. So it repeats this cycle every pi units horizontally. So if there is an answer to the function at pi over 8, there's going to be another answer to the function pi units later, right? Pi units to the right or to the left of that. So if we add pi to pi over 8, so pi over 8 plus 8 pi over 8, we get 9 pi over 8. And if we add the period to this answer, we know the function will be back to that exact same height, that exact same y value at that point. Right, so 3 pi over 8 plus 8 pi over 8 is 11 pi over 8. So just add the period to any answers and you get more answers because it's a periodic function. So we can get our first two answers by cutting these ones in half, And then we can generate these two answers by adding the period of the function to these two answers. So let's go ahead and try and solve some of these algebraically using that understanding of this new sine of 2x function. Now let's complete example 1, where we actually algebraically solve a double angle trig equation. So example 1 says sine of 2 theta equals root 3 over 2, where theta is between 0 and 2 pi. So when solving trig equations, the questions will usually specify what domain it wants the answers between, so we only want the answers between 0 and 2 pi. Right? There's an infinite number of answers to trig equations because trig functions are periodic functions. So they have pattern at y values that just repeat over and over and over again. So we just want the answers between 0 and 2 pi. So we need to figure out what values for theta make this equation true. The first thing we should do is we should change this equation to a linear trig equation by using a let statement. And that'll create an equation that we know how to solve from previous sections in this unit. So I could make a let statement that says let 2 theta equal any parameter we want. I'll use x. Let 2 theta equal x. And now look at what the equation looks like. It's sine of x equals root 3 over 2. And that's just a linear trig equation that we know how to solve from earlier in the unit. So we can use our cast rule and reference angles to find the answers between 0 and 2 pi for this equation. So we have a positive trig ratio. Oh, and I should mention, right, when we're finding answers to trig equations, we always want to give exact answers if possible. So if we can create this ratio from a special triangle, we can get the exact answer. We don't have to use our calculator and inverse sine to get approximate answers, right? We can get exact answers. Since I have a positive sine ratio, I can solve this equation by placing terminal arms in the two quadrants where sine is positive. So sine is positive in this quadrant here, quadrant 1, and this quadrant here, quadrant 2, and cast rule tells me that. So I know that if I were to place a reference angle in those two quadrants, where the reference angle gives me this ratio, I can find the two answers to this linear trig equation. So I'll place a terminal arm in those two quadrants, here and here, and now I figure out what reference angle creates this ratio. Well, sine of what equals root 3 over 2? Let's look at our special triangles. Sine from right here, sine from this angle, opposite over hypotenuse, is root 3 over 2. So if I place that reference angle, pi over 3, in those two quadrants, I can use that information to figure out the principal angles that give me this ratio. So let me first start by labeling the angles around the Cartesian grid. And now that I have the angles labeled, let's figure out the principal angles to those two terminal arms. So I need the principal angle. That means angle from positive x-axis to there, counterclockwise, and from the positive x-axis to here. So to get those two angles, well, the first one, I'll call this x1, and I'll call this second one x2, just to distinguish between our two answers. So x1, since we're in the first quadrant, the reference angle and the principal angle are exactly the same, so x1 is pi over 3. But x2, to calculate the angle between here and here, notice I fell pi over 3 short of going a full pi radians, so I can just do pi minus pi over 3 to get that answer. So pi minus pi over 3. So pi, with a common denominator to this one, it's 3 pi over 3. So 3 pi over 3 minus 1 pi over 3, that's 2 pi over 3. So if I were to rotate either pi over 3 or 2 pi over 3, I would get a sine ratio of root 3 over 2, right? Sine of pi over 3 and sine of 2 pi over 3 are both root 3 over 2. So we've solved this equation that we made. But keep in mind, that's not the overall equation we're trying to solve. We're trying to solve this equation, sine of 2 theta equals root 3 over 2. So we now have to plug back into our let statement and solve for theta. And let me just show you graphically in Desmos what I'm talking about again. So here's sine x. What we've solved for so far is when is this equal to root 3 over 2. So let me just draw a horizontal line through root 3 over 2. So we've solved for these 2 points right here. We got pi over 3 and 2 pi over 3. But keep in mind, these are not the answers we're looking for. We're not looking for when is sine x equal to root 3 over 2. We're looking for when is sine of 2x equal to root 3 over 2. And how are these graphs related? Well, this one is a horizontal compression by a factor of a half. So each of the points, like this point right here, this max, is now half the distance to the y-axis, right? Instead of it being pi at pi over 2, this max, the graph of sine of 2x the max is at pi over 4. It's half the distance. So how is that going to relate the answers? Well, this answer, pi over 3, is now going to be over here at pi over 6, and so on. So the answers are cut in half. So I now need to figure out when is sine of 2x equal to root 3 over 2, so I just have to cut these two answers in half. They've been horizontally compressed by a half. And if we plug back into our let statement and solve it algebraically, it'll do that for us. And let me show you what I mean. So our first answer for x, let's plug that back into our let statement. And let me remind you, our let statement was let 2 theta equal x. We now have two answers for x. Plug them both back into this equation. So 2 theta equals pi over 3, and 2 theta equals 2 pi over 3. And I'm just putting these subscript 1 and 2 to distinguish between my two answers for theta. So I plugged both of my answers for x back into my let statement. Now solve both of these for theta by dividing the 2 over. Right? What we're doing here is we're cutting our answers in half, which graphically should make sense because it's a horizontal compression by a half. And I get theta 1 equals pi over 3 divided by 2. That cuts it in half to pi over 6. And divide 2 pi over 3 by 2, and I get theta 2 equals 2 pi over 6, which is just pi over 3. So I found my two answers. Let me get rid of the original sine function. So I found these two answers, pi over 6 and pi over 3. I have found those two answers. But we want all of the answers between 0 and 2 pi. And notice this function does 2 cycles between 0 and 2 pi, right? Because it's been horizontally compressed by a half. So I found these two answers. I now need to also find these two answers. These two answers are also between 0 and 2 pi. And remember, since this function is periodic, the distance between this answer and this answer is going to be equal to the period of the function, and the distance between this answer and this answer is going to be equal to the period of the function. So all I have to do now is add the period of the function to these two x values, or theta values, and I get more answers to the equation. So I'm going to make a note here of what I'm going to do. So add the period of sine of 2 theta, and the period of sine of 2 theta equals 2 pi over 2, right? You always do 2 pi divided by the k value, so pi. So add pi to both of our previous answers, theta 1 and theta 2, to get more solutions to our equation. To get more solutions to sine of 2 theta equals root 3 over 2. So I can take this answer and I can add the period pi to it and get another answer. So I'll call it theta 3. I can calculate that by taking my theta 1 answer and adding the period. Add pi. So pi over 6 plus pi, and think of pi as 6 pi over 6 so that you can think of it with a common denominator. So I have, sorry, let me write that pi better. So I have pi over 6 plus 6 pi over 6, that is 7 pi over 6. And I can also generate another answer by adding the period to theta 2. So I'll say theta 4, my fourth answer, equals theta 2 plus the period. So it equals pi over 3 plus pi. So 1 pi over 3 plus 3 pi over 3, that's 4 pi over 3. So I found more answers. So let's look back at the graph. We now just found this answer as well, 7 pi over 6, and we found this one as well, 4 pi over 3. And if I wanted more answers, I mean, those are all the answers between 0 and 2 pi. I mean, there are an infinite number of places where this function is equal to root 3 over 2. We can just keep adding the period to the function. Like, add the period to those two answers, we get these two answers. Add the period to those two answers, we get these two answers, and so on. But we only wanted the answers between 0 and 2 pi. Right? If we added pi to this answer, so 7 pi over 6 plus 6 pi over 6 is 13 pi over 6. That's past 2 pi, so we wouldn't want to include that answer. So you just keep adding the period until you have all of the answers within the specified interval in the question. So let me just summarize what we have figured out here. We have figured out that sine of 2 times pi over 6 is equal to sine of 2 times pi over 3. Right, pi over 6 and pi over 3 were my first two answers for theta. And those are both equal to sine of 2 times 7 pi over 6. and sine 2 times 7 pi over 6 and 2 times 4 pi over 3, and these are all equal to root 3 over 2. And you could check all of these in your calculator, and they should all be equal to root 3 over 2. So we found all the angles that when you double them, we get a sine ratio of root 3 over 2. Example 2. Let's solve this double angle equation. Cosine of 2 theta equals negative 1 over 2, but once again we only want the answers for theta that are between 0 and 2 pi. So when we're solving this question, it's going to be just like the process from the previous example, so I'll go a little more quickly this time. But the steps are the same, right? So we're trying to figure out what angle, when we double it, we get a cosine ratio of negative 1 over 2. So the easiest way to start this is to use a let statement. Let's say let x equal 2 theta. And then we'll figure out what values of x have a cosine ratio of negative 1 over 2. And once we know that, then we can actually solve for theta. So our new equation says cos of x equals negative 1 over 2. And this is a linear trig equation that we know how to solve. So first of all, we have a negative cosine ratio. So we have to figure out between 0 and 2 pi, right? I'll label the angles on the Cartesian grid. So between 0 and 2 pi, what are the two angles that have this cosine ratio of negative 1 over 2? So we should also remember your special triangle. So let me draw the special triangle down here. And looking at this special triangle, we can figure out what reference angle has a cosine ratio of 1 over 2. So cosine means adjacent over hypotenuse. So cosine from right here would be 1 over 2. So what we do is we take that reference angle and we place it in the two quadrants where cosine is negative, here and here, because that will be able to create us the cosine ratio of negative 1 over 2. So we place the reference angle of pi over 3 in those two quadrants. So I'll place pi over 3 here and here. So I'm going to get two answers for x. I'll call this one x1. I'll call this one x2. And the reference angles, right, were pi over 3. So remember, reference angle is angle between terminal arm and x-axis. So pi over 3 here and pi over 3 here. And now I have to figure out what is the principal angle of rotation to get to these two terminal arms. And by principal angle, I mean the angle from here counterclockwise to here. And for x2, the principal angle would be from here counterclockwise to here. So to get those two angles, I'm going to have to do a little bit of calculation. So x1 would equal, well, I fell pi over 3 short of going a full pi. So do pi minus that pi over 3, and that will give me the principal angle to angle x1. So pi minus pi over 3. Think of pi as 3 pi over 3. So 3 pi over 3 minus 1 pi over 3, that's 2 pi over 3. And now let's calculate x2. I went a full pi and then another pi over 3. So do pi plus pi over 3 for this one. Pi plus pi over 3. So that gives me 4 pi over 3. So I have my two angles that have a cosine ratio of negative a half. But what I'm interested in is what angle theta do I have to double to get 2 pi over 3 and 4 pi over 3 so that I get a ratio of negative a half for this equation. So to figure that out, we take these two answers and plug them back into our let statement that we made. Because keep in mind, each x is actually equal to 2 theta. So I can say, so I'll write a reminder of the let statement. Here is our let statement. X equals 2 theta. We got two answers for x, so plug them both back in. So we got 2 pi over 3 equals 2 theta. And we also got 4 pi over 3 equals 2 theta. And I'm just writing the subscripts 1 and 2 to show the difference between my two answers. Divide the 2 over on each of these equations we made to isolate theta. So I get theta 1 equals, so I do 2 pi over 3 divided by 2. That gives me 2 pi over 6, which reduces to pi over 3. And this one, when I divide the 2 over, I get 4 pi over 6, which reduces to 2 pi over 3. So those are the two answers in the first cycle of sine of 2 theta. Remember, I can get two more answers by adding the period of the function to these answers, right? There's an infinite number of answers that will give us that cosine ratio. Just add the period to any of your answers and you get more. And we want all of the answers between 0 and 2 pi. And remember, this function is going to do 2 cycles between 0 and 2 pi. Let me just bring this up in Desmos quickly to make sure you know what we've found. Okay, here in Desmos, I have a cosine function graphed. And what we did first was we figured out where is a normal cosine function equal to negative a half. So it's equal to negative a half right here at 2 pi over 3 and right here at 4 pi over 3. And then we figured out, okay, well, we actually want to know when is cosine of 2x equal to negative a half. So we know that that would horizontally compress this function by a half, and let me just show you that. So the graph of this one is horizontally compressed by a half. So we divided each of our answers from cos x equals a negative a half by 2, and it got us these two answers, pi over 3 and 2 pi over 3. But notice this function does 1 cycle and another full cycle between 0 and 2 pi. So we also now need to get these two answers over here. There's 2 more places between 0 and 2 pi where the cosine of 2x function is equal to negative 0.5. So we take these two answers, add the period to them, and it gives us these two answers. So let's go ahead and do that. So let me just summarize here what I just showed you in Desmos. Add the period. And remember, we always calculate period by doing 2 pi over the absolute value of k. And in this case, the k value is 2, right? It's a cos of 2x function. So the period is pi. So we add the period of pi to theta 1 and theta 2 to get more answers. To get more answers to cosine of 2 theta equals negative a half. Right? If I add the period to this one and to this one, I get 2 more answers. So let's do that. I'll call them theta 3 and theta 4. So theta 3 equals, I take my first answer and add the period. And my first answer was pi over 3. So do pi over 3 plus pi, that's 4 pi over 3. And to get my fourth answer, I'll add the period to my second answer. So theta 2 plus pi. And my second answer was 2 pi over 3, so I'll do 2 pi over 3 plus pi. 2 pi over 3 plus 3 pi over 3, 5 pi over 3. So I've come up with 4 answers. And there, like I said, there's an infinite number of angles that would satisfy this equation. I found all of the angles within 0 and 2 pi. Now, if I added the period to these two, I would get more answers, but they wouldn't be within the interval stated in the question. So always pay attention to the interval in the question and keep adding the period until you've gotten all the answers within that interval. So what we have just figured out here, we've figured out that cosine of 2 times any of our answers for theta. So either pi over 3 or cosine of 2 times 2 pi over 3 or cosine of 2 times 4 pi over 3 or cosine of 2 times 5 pi over 3. Any of those would equal negative a half. And you could check any of these on your calculator and they should all give you a ratio of negative 1 over 2. Example 3, tan of 2 theta equals 1. So this is the first tan double angle equation we have, and we only want the answers for theta between 0 and 2 pi. This equation is going to be slightly different than example 1 and 2 because the period of tan x is different than the period of a sine x and cos x function, right? A normal sine x or cos x function has a period of 2 pi, which means the period of sine of 2x and cos of 2x is pi. But this is a tan double angle function. So the period of a tan function is not 2 pi. Let's have a look at a normal tan x function in Desmos. Here it is. Notice that the pattern of y values that repeats is this section here. That section just repeats over and over and over again. And what's the horizontal length of that cycle? Well, what's the distance between pi over 2 and 3 pi over 2? That's 2 pi over 2, which is just pi. So a normal tan function, its period is just pi. So what does that tell us about the period of a tan double angle function? Well, you consider this a k value, right? Which does a horizontal stretch or compression by its reciprocal. So it does a horizontal compression by a half, which means we have to multiply this by a half, which gives us pi over 2, right? The period of a tan double angle equation is only pi over 2. So I've changed this to y equals tan of 2x now. And notice, what is the horizontal length of one cycle now? Well, what's the distance between 5 pi over 4 and 7 pi over 4? That's 2 pi over 4, which is pi over 2. So the period of tan of 2x, or in this case tan of 2 theta, is pi over 2. So when we're finding the answers to this equation, when is this equal to 1? Once we have our first answers for theta, we're going to add the period to those to get more answers. Let me show you that in Desmos as well. So here's the line y equals 1, and we're interested in when is tan of 2x equal to this. So we'll use our cast rule reference angle stuff to get our first two answers, and we'll get pi over 8 and 5 pi over 8. But after we get those answers, notice we add the period, which is pi over 2, or 4 pi over 8 if we want to think of a common denominator, to this answer. Right? If we add 4 pi over 8 to 5 pi over 8, we get 9 pi over 8. If we add 4 pi over 8 to that, we get 13 pi over 8. So notice we're just adding the period of the tan of 2x function to get more answers in other cycles. This one's also a little unique because if we add the period to our first answer, we're actually going to get the second answer, which we would already have from our cast rule and reference angles. But to that second answer, just add the period, and to that third answer, just add the period, and then we get all of the answers between 0 and 2 pi. There's another answer over here, but that's past 2 pi. So let's go ahead and do this algebraically. So we're finding the ratio of 1, and this is actually nice because we can get an exact answer for this one again, right? If we couldn't get an exact answer from a special triangle or a unit circle, we would have to use inverse tan ratio on our calculator. But let's start by making our let statement. So let 2 theta equal whatever parameter you want, I'll call it x, and our new equation says tan of x equals 1. And like I said, we can create this ratio from a special triangle. Let me remind you of that special triangle. It's the isosceles special triangle, where the side lengths are 1, 1, root 2. So tan from right here equals 1 over 1. So tan of pi over 4 equals 1. So what we do is we place that reference angle pi over 4 in the 2 quadrants where tan is positive, right? Because we have a positive tan ratio here. And tan is positive here and here. So I'll place a pi over 4 reference angle in those 2 spots. I'll place pi over 4 reference angle here and a pi over 4 reference angle here, and then I'll calculate the principal angle for each of those. So for this terminal arm, the principal angle is just pi over 4. If you're in quadrant 1, the reference and principal are the same. But if I'm calculating the principal angle from here all the way over to this terminal arm, notice I went past pi by pi over 4. So let me write these two answers. I'll call this one x1, this one x2. So x1 is equal to pi over 4, and x2 would equal pi plus pi over 4. So 4 pi over 4 plus 1 pi over 4, that's 5 pi over 4. So I have two answers for x. So these are the two angles that would give me a tan ratio of 1. And keep in mind, I want to now figure out, well, to get these two angles in this equation, I have to figure out, well, what angle do I double to get those? So sub them back into your let statement, and then we'll figure that out. So keep in mind, our let statement was let x equal 2 theta. So we had 2 theta equals pi over 4. That was one of our answers for x. And we also would get 2 theta equals 5 pi over 4. That's another one of our answers for x. And now isolate theta in each of those equations we made. So divide the 2 over. Theta 1 equals pi over 8. And theta 2 equals 5 pi over 8. Now let me remind you graphically what we have found here. So if you look at this graph, we have found this answer, right? Pi over 8 is an angle that if we plug it into this equation, then we get a tan ratio of 1. And also 5 pi over 8 is an angle if we plug it into this equation. We get a tan ratio of 1. But we want all the answers between 0 and 2 pi. So not only do we need these two answers, but we also need this answer and this answer. And the distance between any of these answers, since it's a tan function, the distance is the period of the function, which is pi over 2. So if I add pi over 2 to my first answer, I just get my second answer. So no point in doing that. Just add pi over 2 to your second answer to get your third, and add pi over 2 from your third answer to get your fourth. So I'll make a note for you here. Add the period of tan of 2 theta, which in this case is pi over 2, to theta 2 to get more answers. And you keep adding the period until you've found all the answers within the interval the question specifies. And this question said between 0 and 2 pi. And hopefully you understand I'm not going to bother adding pi over 2 to this because it'll just give me this answer, and I already have that. So let's calculate theta 3 by doing 5 pi over 8 plus the period of the tan of 2 theta function, so plus pi over 2. And that gives me 5 pi over 8 plus 4 pi over 8. It gives me 9 pi over 8. And if I want theta 4, I can just take theta 3 and add the period, pi over 2. So theta 3 was 9 pi over 8. Add the period of the tan of 2 theta function. 9 pi over 8 plus 4 pi over 8 is 13 pi over 8. And notice that's less than 16 pi over 8, so it's still within the 0 to 2 pi interval. If I added 4 pi over 8 to this, I'd get 17 pi over 8, which is past 2 pi, so we don't need that answer. So my 4 answers, I'll summarize it here. So tan of 2 times pi over 8, or tan of 2 times 5 pi over 8, or 9 pi over 8, or 13 pi over 8. Those all have a tan ratio of 1. So that's it for all the examples we're going to do in this lesson. I just want to make sure you know a couple things before you try the practice questions. Number 1, for all of these examples, the ratios we were solving for, so root 3 over 2, negative 1 over 2, and 1, we were able to create those with our special triangles. So if you were given a ratio, so like let's say let this say cos of 2 theta equals 2/3. If you were given a ratio that you couldn't figure out using a special triangle, you wouldn't be able to get an exact answer for it, so you'd have to use your calculator, use the inverse cos function to help you get the approximate answers. So in the workbook, in the practice questions, there's some examples where you'll be able to get exact answers using special triangles, and there's some answers where you won't be able to, so you'll have to use your calculator to get approximate answers. But always get exact answers if possible. Right, for this one, when we were solving this equation, you could use your calculator, do inverse cos of -1/2, and it would give you an approximate answer. But it's better if we use our special triangles to get the exact answers. The other thing I want you to know is in the workbook, there's some practice questions where it's not necessarily a double angle. It could be a triple angle or a quadruple angle. So for those questions, just figure out what the period of the transformed function will be. Get your first answers using a let statement, and then just add the period of the transformed function to keep getting more and more and more answers until you get all of the answers between 0 and 2 pi. So I hope those practice questions go well for you. Make sure you go to the link in the description to get them, and that's it.